All right, guys, good afternoon. Welcome. It's Friday. Should be exciting for you. I hope everything went well yesterday with the midterm. I'll hopefully have those things graded here pretty soon. But today we are starting on section 4.2. On Monday, we started on section 4.1, which was composite functions and looking at their domain. So today we're actually going to go back and review a topic on one-to-one functions and also jump in and talk about some inverse functions. So just looking right here, these are just some of our objectives here for this section. You guys can go through and read that. All right, so we're just going to jump right in and get started. All right, so if you guys remember back when we first started talking about functions this semester, we started talking about how to determine whether a function was a function, and then also how to determine whether or not a function was one-to-one. Now, if you go back and remember, a function is a function if no x values repeat if you were looking at a set of ordered pairs. All right, now the same thing or similar for a one-to-one function. All right, except for first we need to determine whether or not, first of all, it was a function. If it was, then we could determine whether or not a function was one-to-one. If we're looking at a set of ordered pairs, we're looking at to see if my y values repeat or any of my range values repeat. So if you look here, there are four different ways to represent a function. A mapping, which is just going to be a picture of a set of information, a set of ordered pairs. You could look at it as a graph. Remember, graphically, if it's a function, it passes the vertical line test. If it's one-to-one, it passes the horizontal line test. All right, or by looking at an equation. All right, so what we're going to do, we're going to look at first a mapping. This is considered to be a mapping. So here are two different functions. How do we know they are functions? All right, so first of all, we're looking to see if any of my x values repeat. All right, so the first one we have different states in their population. The second we have different animals and their life expectancy. All right, so let's just look here. So Indiana has one line to it, which means if I were to write that as an ordered pair, it'd be Indiana, comma, its population. My second would be Washington, comma, its population, South Dakota, comma, its population, North Carolina, comma, its population, Tennessee, comma, its population. That's if I wrote those as ordered pairs. But notice, I've only got one line coming from each of these. All right, so that means this represents a function. All right, so if we look down at some of our questions are going this way. It says, what is the state with a population of 761,063 people? Well, just by looking at it, you can go to look at your population, and it only goes back to one specific x value, which would be South Dakota. So we'll just write here, I'm just going to write South Dakota. And again, I apologize here, guys. We are using a mouse, so the handwriting is not the greatest. So we got South Dakota. All right, so the second one. Now we're going to look at my second particular graph. All right, it says which animal has a life expectancy of 11 years? Now, if you notice, I've got two different answers here. A dog has a life expectancy of 11 years, and so does a cat, which means this 11 repeats itself. So if I were to actually write this out as ordered pairs, this would be dog, comma, 11, and cat, comma, 11. So my 11 actually repeats. So this actually would not, so this particular example right here would not represent a one-to-one function because my y values repeat. So here I would have to say cat slash dog. Again, I apologize for the handwriting. All right, now this bottom part in here, what is the difference between the two functions? So we kind of touched on it a little bit, but in my first function, every single one of my y values had exactly one x value with it. None of my x values repeated, none of my y values repeated. Now, if we look at my second function, none of my x values repeated. However, my y values did. So we already talked about the dog and cat, but if you look at duck, lion, and pig, all three of those have a life expectancy of 10 years. So that would be duck, comma, 10, lion, comma, 10, pig, comma, 10, rabbit, comma, 7. So my 10 would also repeat. So again, this would not represent a one-to-one function. So this is what a mapping would look like. All right, and this is kind of more of the mathematical definition of a one-to-one function. All right, so if we're looking for any two different inputs in the domain correspond to two different outputs in the range. So once again, that just kind of looks like my y values and making sure they're not repeating. Another way to say it is a function is one-to-one if no y in the range is the image of more than one x. Again, saying the same thing where no y values are repeating. And the easiest way I've always found for this is to see, or to set them all as ordered pairs and see if any of them repeat. All right, so looking here, all right, so looking at this mapping. So if you noticed, x1 goes straight to y1. No other of my domain values go to y1, so y1 does not repeat. x2 goes to y2. Nothing else goes to y2, so y2 doesn't repeat. And then x3 goes to y3, and once again, nothing else goes to y3, so this represents a function. It is one-to-one as well. All right, so none of my y values repeat. All right, so let's look at the second one. x1 goes to y1, x2 also goes to y1. So if I were to write those out as ordered pairs, that would be x1 comma y1, x2 comma y1. So once again, my y values are repeating. Therefore, this is not one-to-one. All right, so x3 goes to y3, so we're good there. All right, this last one, I'm looking to see if my y values repeat at all. All right, now first we got to make sure it's a function. Then we can determine whether or not it's one-to-one. All right, so if we look at x1, x1 goes straight to y1. x1 also goes to y2. And then we have x3 to y3. So actually, in this case, I have an x value that repeats, which means this is not a function. Therefore, it is not one-to-one. All right, so it has to be a function first in order for it to be one-to-one. All right, so the first one was one-to-one function because none of the x values repeated, none of the y values repeated. The second one was not a one-to-one function, but it was a function. And this third one's not even a function, therefore it can't be one-to-one. So that's just looking at a mapping. All right, so let's just look at a couple of examples here. Determine whether the functions are one-to-one. So first of all, we have to determine is it a function or not, and then we'll determine whether or not it's one-to-one. So let's look at this first one. All right, so let's make sure it's a function first. So let's see if any of my x values repeat. Well, let's write them out as ordered pairs. This would be 38, comma 57. All right, the second one would be 42, comma 54. 46, I'll just do this to make it a little bit easier. 46, comma 34. We'll put a parenthesis around that. So these are my ordered pairs. The next one will be 55, comma 38. And the other one will be 61, comma 38. All right, so first, let's see if any of my x values repeat. Well, none of those actually repeat. All right, so this is a function. So I'm just going to put f. I'm going to say yes. It is a function because none of my x values repeat. 38, 57, 42, 46, 455, 61. None of those repeat. So let's just see now if it's one-to-one. I'm just going to use that as my denotation for one-to-one. So one-to-one, I'm looking to see if any of my y values repeat. Well, 57 doesn't repeat. 42, 54 doesn't repeat. 34 doesn't repeat. However, 38, if we look at that, 38 does repeat. 38, let's see if we can't erase this a little bit. There we go. Makes it a little bit easier. 38 occurs twice. Notice we've got 55, 38 and 61, 38. So my 38 actually repeats. All it takes is 1. So yes, it's a function, but no, it is not one-to-one because I have a y value that repeats. Ordered pairs are the easiest way to look at it. All right, so first of all, is it a function? Do any of my x values repeat? Well, I've got a -2, -1, 0, 1, 2. So first, is it a function? We're going to say yes, it is, because none of my x values repeat. And then we're going to look to see if it's one-to-one. So now that it's a function, let's determine if it's one-to-one. All right, so let's look at my y value. So I got 6, a 3, a 2, a 5, and an 8. None of those repeat. Therefore, yes, it's a function, and yes, it is one-to-one. So that's just an set of ordered pairs. Those are probably the easiest to identify. Now, when we're looking at the graph of a function, like we brought up earlier, to determine if something is a function, we use the vertical line test. And then to determine if something is a one-to-one function, we're going to use the horizontal line test. All right, so that's what we're going to be looking at here. So first, we'll still do the vertical line test, and then we'll also do the horizontal line test to see if it is, in fact, a one-to-one function. All right, so for each function, use the graph to determine whether the function is one-to-one. So first, let's see if it is, in fact, a function. So let's take this first one. So if I drew a vertical line here, if I drew one here, if I drew one here, here, every single one of these lines is only crossing my graph one time. Therefore, yes, it's a function. All right, so again, that's the first kind of important thing. It's got to be a function first of all. All right, so yes, it's a function. And again, I'm sorry for the handwriting. All right, so let's see if it's one-to-one. So let's see if it actually passes my horizontal line test. Let me erase some of this. So we got our vertical line test. Check. Let's check my horizontal line test. Let's draw one line. Boom. Right away, hits it once there and once there. So if it hits the graph more than once, it is not one-to-one. So notice again, it hits here and it intersects here. More than once means it is not going to be one-to-one. All right, so there's my first example. So let's look at my second one. So first of all, we got to look to see, is this in fact a function? So let's see if it passes the vertical line test. So let's get the tool out again. All right, so vertical line touches once, touches once, touches once, touches once. Doesn't matter where I draw my vertical lines, it's always going to touch it only one time. So yes, this is in fact a function. So now let's see if it's actually one-to-one. So similar concept, now we'll just do a horizontal line test. So once, 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 once. We're good. All right, so if you guys look through there, you notice that every horizontal line only touches it one time. So we'll say 1-to-1 is yes. As long as it only touches the graph one time, yes, it is 1-to-1. Now, some of you may have kind of looked right here around the origin. It looks like you might have a line that intersects more than one spot on the graph. However, if you actually zoomed in on that particular graph and looked at the values, you would see that it actually is not intersecting more than once. So yes, that actually would be a function, and it will be one-to-one. So that's looking at one-to-one function. Now what we're going to do is we're going to go through and look at inverse functions. Now, there's a few different ways to determine if something is an inverse. All right, one of those is by looking at a map or set of ordered pairs. Inverse just literally means you are flipping your x's and your y's. That's all you're doing. So once again, ordered pairs are probably the easiest way to see this. Looking at a map, also pretty easy because again, you're just taking your x and y values and you're flipping them. All right. Now, we've talked kind of about inputs and outputs just a little bit, and sometimes some of you may have heard in the past about a function being a machine. How you're saying you're inputting your x values and you're outputting your y values. You're inputting your domains and you're getting out your ranges. All right, so your outputs are your y values, your ranges, your inputs are your domains, your x values, etc., etc. All right, so the inverse is actually going to get the input and then output it. So it actually your x and y's flips. You're actually inputting y's and you're getting x's out, which is counterintuitive what you're used to. So, for example, if we look at this first one, we said if f of x equals 2x plus 5, then f of 3 equals 11. So what that means is if I took 3 and I plugged it in, let's just do that real quick. So 2 times 3 is 6. 6 plus 5 equals 11. So f of 3 is 11. So here, 3 is your input, your x value, and 11 is the output. That would be your y value. The inverse would undo what f does and receive as input 11 and provide your 3 as output. So basically, again, you're just switching your x and your y value. 3 was your original x, 11 was your y. You would be taking those and flipping them. So 3 was your input, 11 was your output. Now if you flip those, 11 would be your input, 3 would be your output. So you're just flipping your x and y. All right? So let's look at an example down here. So finding the inverse of a function by a map. So this one's the same one that we were looking at earlier. All right, so it says find the inverse of the following function. Let the domain of the function be certain states and the range be the state's population. State the domain and the range of the inverse function. So my original domain. So let's make a, all right, so my original domain, and this would be much easier if I wasn't using a mouse. Boom. So my original domain is going to be all of my states. So I would literally write out Indiana, I'm just going to abbreviate, Washington, I abbreviate, South Dakota, North Carolina, come on and raise up, and Tennessee. So those would be my original domains. I don't know why I'm actually writing that out. All right, my first original ranges are going to be my population. All right, so these are all my x's, these are all my y values. So those are my original domains, these are my original population. So instead of rewriting all those, and I don't know why I can't even draw a circle, let's try this again. So these are my original populations. We'll stick to squares and rectangles. All right, so all of those are going to be my original populations. I would literally list them out. Now, those are my original. Now, if I was to find the inverse, I'm taking all of this right here, all of my x's and all of my y's, and I am flipping them. So these are going here, and these are going there. So to find my inverse, I'm going to flip all of my x's and all of my y's. So over here, we're going to put the inverse. These are going to be my inverse values. Now, what that means is all of my x's and all my y's are flipping. So now my original domains are going to become my new ranges, and my original population, my original range values will become my new domain. So my new domain is going to be all of my population, and we would list out every single one of these individually. We wouldn't just write population, so we would list out every single one. And then my new range of my inverse, I'll just write starting cursive, is going to be all of my states. Maybe not. All right, so I'm going to list out every single one of those as well. So again, my inverse is going to take all of my x's and all of my y's and flip them. All right, so that's just looking at a mapping example. Now, ordered pairs are probably going to be the easiest way to find an inverse. We literally switch all of my x and y's. I mean, literally. All right, so these are my original ordered pairs. So my inverse would be, if I take this first one, I'm going to flip my x and y. So my inverse here would be negative 27, comma, negative 3. There's my inverse. My inverse for my second point, negative 8, comma, negative 2. Flip it. All right, now this third one, I'm going to flip them, but it's not going to look like I did because they're the exact same value. All right, but negative 1, negative 1. Same thing here, 0, 0, I flip them. So my inverse coordinate there would be 0, comma 0. And then 1, comma 1. And then 8, comma 2. And then 3, comma 27. Psych. Making sure you guys are awake. Let's try that again. So my last one will be 27, comma 3. So those are my inverse values. So once again, ordered pairs are probably the easiest because you're just taking your ordered pairs and you are flipping them. All right. Now let's look at an actual function. All right. For a function to be one-to-one, then the following has to be true. Your domain is going to be equal to the range of your inverse. So again, when I had all my x's, I take the inverse. Those now become my y's. So my domains of my original become my ranges of my inverse. And then vice versa. My original range values, my original y values now become my x values, or my domain values in my inverse. All right? So what we're going to do is we're going to look at finding some inverses today, and then we are going to take that and verify. Here's a keyword, verify. Now, some of you don't know verify. That just means check or show that or prove that these two pieces are actually inverse. Now, at the very end of the 4-1 notes we did on Monday, we actually did some verification. The very last thing we did there was to show that two functions were inverses of each other. And if you remember that, which some of you may not, so we've had a lot of time between them, f of g of x was equal to x, and then g of f of x. So that goes back to my composite functions, also equaled x. So when I took g of x and plugged it into f of x and simplified, I got x. And when I took f of x and plugged it into g of x, I also got x. So those two things have to be true in order for two functions to be inverses of each other. All right, so let's look at these two functions. So first, let's do f of g of x. So that means, if you go back and remember, I'm going to take g of x and I'm plugging it anywhere I see x into f of x. So that means in the place of this x, I'm going to put the cubed root of x. So I've got the cubed root of x. Boom. Cubed. All right, because there's my cube, so it's the cubed root of x cubed. Now, just like when I have the square, when I'm squaring a square root, those cancel each other out. So same thing here. A cubed root cancels out a cubed, which means I'm just left with x. That's what I want to see. All right, so let's now go the other way. Let's now do g of f of x. So that means now, let's kind of erase this so we don't get too confused. So now g of f of x means I'm taking f of x and I'm going to plug it into g of x. So I'm taking this value here and I'm plugging it into that value. So that's going to look like the cubed root of, and I'm going to plug in an x cubed. There we go. Same thing's going to happen here. When you take the square root of something squared, they cancel each other out. Same thing when you take the cubed root of something cubed. So once again, I'm left with x. So that works. That's what I was looking for. So because of that, these two functions are inverses. So we would say, yes, they are inverses. Boom. All right, so there's that first one. All right, so what I want you guys to do real quick is go through and verify the second one. All right, now what I've done is I've copy and pasted the exact problem that we did on Monday in the 4-1 notes, and this is the exact one we did. So your original, and actually I just now realized that they are not actually the exact same problem, so that is my bad. So I'm actually going to go back and delete this real quick. So boom, and there we go. So let's try this again, shall we? All right, so f of x, to verify that they're inverse, I want to do f of g of x first. And I'm again looking for x. And then I want to do g of f of x. And once again, I am still looking for x. All right, so if I get those two values, that means that these two functions are in fact inverses of each other. So the first one, f of g of x, means I'm taking f inverse of x, which we're going to call that g of x. That can be called g of x as well. All right, that's how they denote inverse is f negative 1 of x. So I'm going to take that piece and I'm going to plug it back into my original. So I'm going to set up 2 times, in place of that x, I'm going to plug in a 1/2 times x minus 3 and then plus 3. All right, so now you can do this one of two ways. I'm going to do it a quick way. All right, if you multiply 2 times a half, those cancel each other out. You're just left with a 1. All right, so if we do that, that means I'm left with x minus 3 plus 3. Those minus 3 and that plus 3 will cancel. Therefore, I am left with x. So, once again, that's what I'm looking for. We're good. We bueno. Next thing we're going to do is do g of f of x. And I'm going to go up here and erase this piece here. Alright, so next we'll do g of f of x, or plug my original back into my inverse. So same concept. Now I'm going to take my original and I'm going to plug it in here. Alright, so that means I've got 1/2 times, in place of my x, I'm going to put a 2x plus 3, and I've got my minus 3. It's 1/2 x minus 3. So similarly, 3 minus 3 is 0. So I've got half of 2x. Well, half of 2 is just 1, or 1x. So once again, they are inverses. So we verified that. So we did f of g of x. That's the first thing we can do. And then we did g of f of x, or just plugged in my original back into my inverse. So that's looking more at an algebraic function. All right, now if we're going to look at the graph of inverse functions, now going back and looking at some basic graphing techniques. All right, when we're looking at whether or not a graph or two particular graphs of functions are inverses, we're looking to see if those particular functions are symmetric with respect to the line y equals x. So it's symmetric over that line y equals x. And I'm going to try and do my best sketch here. So if I'm looking at that, so there's a line, there's looking at my graph. The line y equals x is that line going through 0, 0, and it has a slope of 1. All right, so that would be the line y equals x. So it's symmetric over this particular line here. That's how we're looking to see if a graph is going to be the inverse. All right, so the original is reflected over here. All right, so the following figure illustrates this result. So if you see right here, it kind of looks like a little DNA strand, but this is my line, y equals x, right here. So there's that line. So I'm looking to see if my original function is symmetric over that particular line. All right, so for example, this point is reflected over here. So notice A3 and B3. Remember, inverses means your x and y values swap. So if it was here originally, then my inverse would be B3 comma A3. B3 comma A3. All right, same thing with A sub 2 and B sub 2. If that's my original point, if I reflected it over that line, it should be B sub 2, A sub 2, which it is. And the same thing down here, A sub 1, B sub 1, when it's reflected over that line y equals x, would be B sub 1, A sub 1. So this is a picture of what an inverse function would look like graphically. All right, so let's see what the inverse would look like here. All right, so just by looking at a graph, all right, I'm just going to draw a rough line of where, let's see, we should have a point. Let's see. All right, so we should have a point there. I'm just going to draw where this should be, where my line y equals x should be. All right, so my line y equals x will go right through there. So that's my line y equals x. All right, so the following figure, draw the graph of its inverse. So remember, to be an inverse, we just take my x and y values and flip them. So my original point, so let's look at this first point. This first point is at the point 2, comma 1. So the inverse of that should be the point 1, comma 2. Because remember, we just take my x and y values and we flip them. So if I go to 1, up 2, so right here, that's where my point should be. All right, same thing here. So negative 1, 0, if I take those and I flip them, that should be the point 0, negative 1, which will be right here. 0, negative 1. So that's that point. All right, so we're here. Trying to draw that straight. I guess I could do this right here. We'll just call it again 0, negative 1. And then the last one would be negative 2, negative 1. So the inverse of that would be if I flip those, which would be the point negative 1, comma, negative 2, which would be right around in here. So that'd be the point negative 1, comma, negative 2. So now let's go through, let's connect those. So I've got that one and that one. So if you guys look, that is the inverse function. So once again, I just took all of my original values and flipped them. All right, so my original ordered pairs, I flipped them. That's what gave me my inverse. So that's what a graph of an inverse would look like. All right, so now what we're going to do, and this is kind of the bulk of this section. This is probably the most difficult part of this section. We're going to find the inverse of the function. All right, so we've got a function. So once we said before, like we said before, we're going to take my x and y values and flip them, and then we've got to get y back by itself. All right, so that's kind of a little caveat here. Is we're going to take all of my x values, or take my x value, flip it with my y, and then solve for y again. All right, so this first one right here, finding the inverse of 2x plus 3. Now, if you guys already see down here, they've already told me what my inverse is, so I'm going to take this and show you how we get from this to that right there. 1/2 times x minus 3. All right, so that's what we're going to do. We're going to take this original piece and we're going to make it look like that pink piece. All right, so first thing we're going to do, guys, is we're going to take, first of all, change f of x. We're going to make that y, just to make it a little more familiar for you. So y equals 2x plus 3. All right, the next thing we're going to do is we're going to take all of my x values, or my 1x value, and we're going to flip it and change my y value to my x value. So I'm going to put an x here. So we flip my x and y. 2y plus 3. So I flip my x and y. Now I want to get y by itself. All right, so to get y by itself, first I need to take this 3 and move it over. So I'm going to subtract 3 over. So this has become x minus 3. So those can't combine. So I'm just going to be left with x minus 3 equals 2y. All right, so now I still got to get y by itself. So in order to get y by itself, I got to get rid of this 2. Well, because it's 2 times y, the opposite of multiplication, as hopefully you know, is division. All right, so now I've got x minus 3 over 2 equals y. Now, you may not notice it or may not recognize the fact, but this equation right here is actually the exact same equation as that right there. All right, they've just factored out this 1/2, so you could take that right there and make it look like 1/2 times x minus 3. So those, in fact, are the exact same equation. So I have y equals, so the last step would be to write it as the inverse function or inverse function notation. So inverse function of x is going to be x minus 3 over 2, or again, you could say 1/2 times x minus 3. So that's finding the inverse of the function. Now we could go through and verify it. Remember, that's when you're going to do f of g of x and g of f of x to make sure you get x at the very end. All right, so same concept. This is just giving you a step-by-step procedure. All right, the thing we didn't do in this last one was step 3. We didn't verify or check the result by showing that when I plug in my original and my inverse, and I plug my inverse in my original, that I got x, which is what we were doing earlier with f of x, f of g of x, and g of f of x. So those are just my steps. So let's look at one of these. All right, we're going to just do one of these today, and then we will wrap up because I know time is of the essence. We're already at 30 minutes, and I know you guys are probably falling asleep already. All right, but we've got a few examples here, and let's look at those really quickly.